Let's do the trains now. Who doesn't love trains, right? By 2050, number 74 would be the ranking for this drawdown approach on improving trains with 0.52 gigatons in reduced CO2. Net cost of getting this done would be $808.6 billion with a net savings of $313.9 billion, but I will show that there are co-benefits of replacing cars and the cascade effects that may be worth much more. This is just an image of a General Electric Evolution Series Tier 4 hybrid locomotive before being painted at its factory in Fort Worth, Texas. The Tier 4 series of diesel-electric locomotives are the most efficient in the world with respect to emissions and can move 1 ton of freight 500 miles on 1 gallon of fuel. 1 ton of freight 500 miles on 1 gallon of fuel. The 440,000-pound behemoths are designed to transport such heavy loads that aerodynamics would have virtually no impact on increased efficiency. The locomotive incorporates regenerative braking, so you get energy back from the braking process, which captures and stores energy in batteries along with 8,000 other fuel-saving solutions. So we are headed in a great direction, right? Just to orient ourselves, passengers carried in terms of passenger kilometers in 2014. So these are passengers carried by railways, are the number of passengers transported by rail multiplied by the kilometers traveled. So a handful of countries which should make it easier to target the improvements in the systems, I suppose. So India, which is very heavily dependent on train and has a huge population, obviously going to end up very high at 5 trillion, and then China, Russia, of course US and South America are not so fond of trains for long distance travel, but some parts of Europe are, especially with the high-speed trains that we looked at before. Let's run through some charts here. Tons of oil equivalent in million passenger kilometers in terms of energy intensity of different transport modes in 2017. Here it is showing large cars, aviation, cars, buses, 2 3-wheelers and rail. So rail obviously is very economic in energy intensity. And here being compared to medium trucks, heavy trucks, rail and shipping. So that's the same here. The scales are slightly different, as you can see. So again, the train is really phenomenal for moving passengers and freight, of course. This is grams of CO2 per megajoule tractive energy. So what are the average well-to-wheel carbon intensities for diesel powertrains and electric powertrains using various primary source in grams of CO2 equivalent per megajoule? So this is what trains could choose from. Diesel, electric, of course, depends on where electric come from. Almost all high-speed trains are run on electricity, but as we said, the electricity better be from a good source. Bituminous coal, anthracite, natural gas, renewables and nuclear. So right now the energy is not coming that much from renewables. This is track length by region from 1995 to 2016 for light rail. So light green, metro rail, high-speed rail and conventional rail. And again, North America, Europe is high, China is going gangbusters, India is still not that intense, and Japan, of course. So those 4 countries in the world can focus on solutions till the other countries decide on what to do about train as a mode of transportation or freight carrying. This is kilojoules passenger kilometers, so energy intensities and freight trains. Again, if we could replace trucks with freight trains, that would be great. This is high-speed rail track length in key regions in 2010 and 2017. China going great in terms of increasing its track lengths for high-speed rail. And then there is Europe doing well, Japan and Korea not that much of a change. Korea is doing some bit improvements there in terms of extending high-speed trains, of course. Okay, so that's a repetition of some of the things we looked at before. This is the annual life cycle total greenhouse gas emission savings and time needed to compensate upfront emissions from the building of a new freight train line in high, medium and low potential cases. So rail emissions, high potential, avoided emissions are massive. In medium potential, avoided emissions are smaller but still really quite impressive. And of course low potential areas. I didn't define exactly what that means, but I think it just means where there is a potential to replace the fuels for trucks, truck vehicles, operational costs, rolling stock, infrastructure, and time to compensate emissions shown here in terms of number of years it would take to accomplish the compensation. From this paper, it's showing impacts of a passenger rail system on CO2 emissions. So net CO2 avoided equals credit minus debit. So CO2 emissions produced by rail systems is a debit. So that's traction electricity. CO2 emissions avoided by rail systems in terms of credit. There is mode shifts expected in terms of attraction of cars and bus users to fewer cars and buses because of shifting to trains. Congestion relief, fewer cars and buses in the traffic, so increased fuel savings. Land use, high density, shorter trips, less needed for car use, less need for car use. So you get the point. Globally, overall impact wise, electrification of rail comprises 166,000 miles of track length. If that increases to 621,000 miles by 2050, emissions from fuel use can be reduced by 0.5 gigatons of carbon dioxide. This additional electrification could cost 809 billion, saving 314 billion over 30 years and 775 billion over the lifetime of infrastructure. Prioritizing high usage corridors can lower net costs. Okay, so that's the train story.